two sample proportions test. And it is a z-test, so that's great because it uses obviously the standard normal or z distribution. A couple of things. In doing this test, we need to look at a couple of new things that I have to define for you. So, just as a reminder, your HO and H1 with the two sample proportions test are going to be P1 and P2. Okay, and then of course you could have greater than or equal to, which would go with a less than. And you could have less than or equal to, which would go with a greater than. And finally, you could have an equals, not equals. So you still have one-tailed, left-tailed, right-tailed, or two-tailed tests. But again, we're labeling one of these hypothesized proportions from one sample or population, and the other we'll label as two from the other sample or population. Okay? The next thing I need to tell you is what the test value formula looks like. So let's get that out of the way. It's a little bit more complicated, so I'll have to define a couple of things in it. Okay, so here's what your test value formula looks like. Z equals P1 hat minus P2 hat minus the hypothesized difference in the population proportions, P1 minus P2, all divided by a big square root, and then here's a couple of new terms that I'm introducing, P bar times Q bar, then in parentheses 1 over N1 plus 1 over N2. Okay. So P1 hat and P2 hat are both coming from the sample data. Okay, so this is my sample proportion for whatever we labeled as 1, and this is my sample proportion for whatever we labeled as 2. Okay, now, when we're doing a sample proportion, so if I look at P1 hat for a second, that is equal to x1 over n1. So the number of sample units in that first sample that have a specific characteristic of interest divided by how large that sample was. For instance, if I took this group of students and say there's 30 of you, and I wanted to know how many of you were left-handed, and maybe 4 of you are left-handed, so it would be 4 out of the 30, and that would be my sample proportion for that, left-handedness, okay? So then P2 would be the number of sample units with the characteristic of interest divided by the second sample size. Okay, so that's a reminder on how I get these sample proportions. Okay, the hypothesized difference here is going to be 0 unless otherwise indicated, and I'm not going to have any problems where it's not 0. N1 and N2 are sample sizes, so something that is new that we have not seen before is P bar and Q bar. Okay, so I do need to define P bar. So P bar is you take all of the sample units that have the characteristic of interest in the first sample together with all of the ones that have this characteristic of interest in the second sample. So it's going to be x1 plus x2 divided by n1 plus n2. Okay, so you're like putting them all together in like this one big sample. So you add all of the, if we're doing left-handers from the first group plus all the left-handers from the second group, divided by how big those groups were sample-wise. Okay? And that's pretty much it. If I have P bar, then what do you think my relationship with Q bar is going to be? 1 minus P bar. Okay, so that's how we get that. Q bar, 1 minus P bar. Okay, that's pretty much everything we need, and then it's just a regular hypothesis test, so we'll go through the steps. What I would like to do is do a traditional method one, and also do a p-value one, so we get work on doing both, okay? But once you have the test value formula and you know what distribution to utilize, it's pretty much the same step. So let's take a look at an example here. A recent survey showed in a sample of 80 surgeons, 15 smoked. In another sample of 50 general practitioners, 5 smoked. At alpha equals 0.05, is the proportion of surgeons who smoke higher than the proportion of general practitioners who smoke? Okay, great. So, to do that problem, obviously there's 2 samples. We have surgeons and general practitioners. And then we have proportions, right? The amount that smoked in each sample. So that's our characteristic of interest, smoking. All right, so here we go. Example 1. In a sample of 80 surgeons, 15 smoked. So we have 80 surgeons. And 15 in that smoked. In another sample of general practitioners, we had 50 and 5 smoked. So 50 GP for general practitioners and 5 in that sample smoked. Okay, that's what we're given in this problem. And then it says, is the proportion of surgeons who smoke higher than the proportion of GPs? So is proportion of surgeons higher? Is the question. So that's the question we want to answer at alpha equals 0.05. All right? So as you guys are getting ready for this next exam, it's really important that you're able to identify what type of problem this is, okay? So if I look at this problem for a couple of minutes, the first thing I notice is there's 2 samples, right? There's a surgeon sample and there's a general practitioner sample, okay? Then the next thing that you should notice pretty quickly is it doesn't say anything about mean or average, and it doesn't say anything about standard deviation, right? Is everybody with me on that? It just says, hey, 80 surgeons, 15 smoked. 50 general practitioners, 5 smoked. So that should hopefully start to be obvious that that's a proportion, right? We have 15 out of 80 and 5 out of 50. And then the question specifically states, is the proportion of surgeons who smoke higher, okay? So this is a 2-sample test for proportion. That's what takes you to the type of test it is, okay? And once I know that, then I'm ready to roll. All right, so usually I'll just keep with my, whatever's given first, I'll label as 1. So I'm going to label 1 for surgeons and 2 for general practitioners. And then I'm ready to move. So HO, H1, we're looking at P1 versus P2, P1 versus P2, and I have to get this right. So the proportion of surgeons higher. So if I label 1 as surgeons and I want 1 bigger than 2, that's going to be right there. P1 bigger than P2, right? Because we're testing the proportion of surgeons who smoke, and I label that as 1, higher than general practitioners, okay? So I'll put what that means. Proportion of surgeons who smoke is higher. Great, then the opposite, less than or equal to for my HO. And I'll be done with my null and alternative hypothesis. Great, based on this, because I chose 1 and 2 this way, I have a right tail test, okay? If somebody else had done general practitioners as 1 and surgeons as 2, they would have a left tail test, but the work and their answer is going to be identical, okay? Except they'll be on the other side, that's all. And that can definitely happen, right? So it just depends on our labeling. Great, step 2, critical value. This is a z-test. So I open up my z-distribution. I have a right tail test. And I have alpha is 0.05. So I need to read off that to critical value. So you go to your z-distribution. We've done this a million times. If you want 0.05 area in the right tail, then this area has to be 0.9500. So I'm on the right side of my z-distribution table, and I'm trying to find the closest thing I can to 9500. And it's awesome if it's in there, but often it's not in there. And this one's right in between 9495 and 9505. So this is going to happen at 1.645. Okay? And you guys can't waste time. When we get to the test on, next Friday, that should take 5 seconds, right? You can't waste time trying to figure out your critical value, okay? Great, move to the test value. So that's the new stuff today. Write down that big formula that I just gave you, and we have to work it out, okay? So the first part of that formula is P1 hat minus P2 hat. So surgeons, we had 15 out of 80 that smoked. That's my P1 hat, okay? Minus my P2 hat. We had 5 out of 50 So my general practitioners, we had 5 out of 50 that smoked. Minus the hypothesized difference between the population proportions, which is 0, divided by a big square root. Okay, then the first part is P bar, right? And how do I get P bar? What do I have to do? I take the number that smoked in the first sample plus the number that smoked in the second sample. So that's 20, right? Divided by adding up both sample sizes together, okay? So 20 divided by 130. Everybody see that? So P bar is adding up, in this case we're talking about the number of people who smoke, so adding the smokers plus the smokers and dividing by the total. That's P bar. Okay? Then what's Q bar? It's 1 minus P bar, right? So if you go to decimal, that might be nice, but if I keep it in fraction, which I'm going to since I've already started in fraction, 1 minus this is going to be 110 out of 130. Okay? And then finally, you have 1 over n1 plus 1 over n2, so 1 over 80 plus 1 over 50. And this is all underneath the square root, so please be extra careful that all of that is still underneath your square roots. Okay? So spend a couple of minutes using your calculator and figure out what that comes out to. Be super careful. All right, I'm getting approximately 1.3452. So see that you get approximately 1.3452 when you put that big fraction together. And again, be super careful down here because you have this number times that thing in parentheses. All of that's underneath the square roots. Okay? If it's easier for you to use decimal, then just use decimal. Okay, whatever's easier. But at some point you should get 1.3452. And once I get that, that's my test value. I plot that on my thing here. 1.645 is my critical region, so 1.3452 is to the left of that, right? So 1.3452. So I do not reject HO, step 4. Do not reject HO. So I'm going to circle HO. I'm going to cross a line through H1. The question is, do the proportion of surgeons who smoke higher than the proportion of general practitioners? We do not find that. Okay, so our answer is no. Based on our evidence, based on our findings, it doesn't appear that the proportion of surgeons who smoke is higher. Okay? So whatever, in your own words, just make sure that it makes sense and answers the question that was asked. Okay, what I would like to do, is there any question on this one first? Let's do another one, and let's use, this was traditional hypothesis tests. Let us also do the p-value method for hypothesis testing. Okay? So let's try another one. All right, example 2. In a recent sample of 100 people, 30% had visited Disneyland. In another sample of 100 people, 24% had visited Disney World. Are the proportions of people who visited each park different? Use alpha equals 0.02 in the p-value method. Okay, example 2. So in a sample of 100, 30% had visited, I'll use DL for Disneyland. In another sample of 100, 24% had visited Disney World. Okay? Alpha equals 0.02, use p-value method. And the question that is asked, what we want to answer is, are the proportions different? Okay, so again, if you read through this problem, it's pretty obvious we have 2 samples. One sample for Disneyland, one sample for Disney World, and we're talking about the amount of people in these samples that visited each of these amusement parks, okay? It says use alpha equals 0.02, use the p-value method, great. And then the question, are the proportions different? That is a pretty big clue that this is a 2-sample proportion test, right? Are the proportions different? Is one proportion different from the other proportion? This is a 2-sample proportion test. Okay. I'm going to let Disneyland be 1 since that came first, and Disney World be 2 since that was introduced second in the problem. And I'm ready to roll. Let's do this. So HOH1. The question is, are the proportions different? How do I label that in my HOH1?
Equals, not equals.
Equals, not equals. Okay, so if they're equal, it's not different. If they're not equal, it's different. Okay? There wasn't a specific claim here. It didn't say, some guy hypothesizes that Disneyland is different. Okay, so we just put not different and different. There was no claim here. Great. Now, remind me, guys, what is the second step in a p-value method problem? Right to the test value. Okay? So go right to the test value. Z equals. Now, this one is kind of nice, but also kind of tricky in the same way. Because it already gives you the proportions. It says 30% and 24%. That is my P1 hat and my P2 hat. Does everybody see that? So we have 0.30. That is my proportion. Okay? Minus 0.24. Minus the hypothesized difference of 0. Then a big square root. Now, once we get to P bar, we have to be careful. Okay? So P bar is the number of people that went to Disneyland plus the number of people that went to Disney World divided by the total. Okay? Now, in an example of 100, 100 is a really nice number, 30% visited Disneyland. So how many people actually visited Disneyland? 30, right. And that's only because it's 100, right? If this was on a test and that sample was like 117, you'd have to calculate 0.30 times 117 to get that approximate number. Okay, so having 100 is a really nice number. Plus, Disney World, there was 100, 24%, so that's also 24. And then this is divided by 200. Okay, so I want to calculate that. That's going to be my actual p-bar value. Okay? So if you want to, go ahead and plug that in your calculator. These numbers are pretty nice, so it should come out to be a pretty nice number. What does this come out to? I'm going to guess 0.27. Did you guys get that? Okay, so P bar is 0.27. And what is Q bar? 0.73, great. Then I have times 1 over 100 plus another 1 over 100, which is 1 over 100 plus another 1 over 100 is 2 over 100. Okay, so that works out really nice too. All right, plug that into your calculator. Be super careful with the square root in the denominator. So let's see what we get here. Okay, I'm getting about 0.9556. 0.9556. Okay, what do I do with that number? Test value, 0.9556. What do I do with it? I put it on my z graph, right? And where is 0.9556? If 0 is in the middle, somewhere on the right. Does everybody agree with that? So now, here's my test value. Because our book only goes 2 decimal places on test values, I'm going to round that guide to 0.96. Okay? Now, I gave you a two-tailed test, and I gave you p-value method. So again, just a reminder, you put it on whatever side it's on, and then whatever, in this case it's on the right side, I need this area to the right of 0.96. Because it's a two-tailed test, I have to multiply it by 2 for the p-value method, okay? That's only for a two-tailed test though. So if I look at 0.96 in my book, or negative 0.96, whatever is easier for you, the area is 1685, okay? So this area here is 0.1685. If this was a one-tailed test, that would be your p-value. But only because this is a two-tailed test, I have to multiply that by 2. So my p-value is equal to 2 times 0.1685. So, what is 2 times 0.1685? Let's see. It's already too high, right? 0.337. So my p-value is 0.337. And that is the end of step 3. Okay, my p-value is 0.337. Step 4. If your p-value is small, you reject HO, okay? More specifically, if your p-value is less than or equal to alpha, alpha is 0.02. Is this number smaller than 0.02? No, not at all, okay? So do not reject HO. So if I do not reject HO, I'm circling HO, and I'm drawing a line through here. Okay? So the question is the proportion of people who visit Disneyland different from the proportion of people who visit Disney World? No. Okay, not according to our findings. There's not a difference. Okay? So 5, to answer your question, no. The proportions are the same. Question?
Can you go over how you did step 4 again, please?
Step 4, if your p-value is less than or equal to alpha, you reject HO. Our p-value is 0.337, our alpha is 0.02. This is much bigger than that, so we do not reject HO. Okay? Okay, so today we did 2 sample proportion tests. We did a traditional hypothesis test, and we also did the p-value method. Okay? On your guys' test coming up, I will only ask p-value problems using the z-distribution. Okay? So if it's a p-value problem, it's going to only be for those using the z-distribution, because that's the one we're most familiar with. Okay? Any questions on this problem? All we have left is variance tests, and then we have our tests.